Hello friends, I'm Ashish Tabari, founder and CEO of Aximize. To our new listeners, welcome. To our old ones, welcome back. In this podcast, we will discuss the role of constraints in formal verification. In our previous podcast, we discussed that formal verification doesn't need an explicit manually driven stimulus generation, as tools do it for you for free. This is great freedom that comes with formal, but with every great freedom comes great responsibility. Simply allowing unconstrained free-for-all input to flow into your design will just cause mayhem. It will cause unforeseen and undesirable failures with your assertions. You will be debugging failures thinking they are design bugs, and it may turn out to be false positives. And one of the biggest challenges with formal verification is scoping out what constraints are needed and how they will be coded in formal for efficient, predictable results. Constraints, as the name suggests, constrains the input combinations not just for one time point, but actually for the whole stream of time points, thanks to the temporal property languages such as SVA and PSL. So the standard way of enforcing the constraints, for example in SVA, is by using the assume directive. We assume certain behaviors to be legal and we define that through an assume property. We could of course define what is not legal. It depends on a given situation, whether we want one or the other or both. Usually defining what is legal is enough to say what is not legal, or the other way around. Now let's look at a specific example. So let us imagine we're going to talk about clocks in our design. And we may want to say that for a specific clock gating scenario, that a clock gating input is always tied off to allow clocks to freely operate and never be gated. Now for some of you who are familiar with low power designs, this is a standard technique of gating off or powering down clocks when you don't need them. Now we could also say that the clock gating input will be enabled only when an upstream sleep signal is sent to a CPU core. If the sleep signal is never sent in, the clocks do not gate. When sleep signal is received, clocks are gated off. Now by not enforcing the constraint, the formal tool will try both combinations for the clock gating input, and it may tie off when it shouldn't, causing assertions that we expect to pass to become fail. By defining an incorrect constraint, for example by making a coding error or an error in understanding the requirement, or even scoping out the requirement in the first place, if we tie off the clock gating when we shouldn't, we will end up missing a bug, as now the formal tool will be checking less, not more, due to this constraint. So the scenarios that we are supposed to check, that when clock gating is actually applied and the clocks must be switched off and therefore we should be checking for additional behavior, will never be verified because we've just tied off the clock gating. Clocks being so simple and so intrinsic to all digital designs, something so fundamental, we can get it easily wrong if we are not careful. Now remember, the quality of proofs is only as good or strong as its weakest link, and constraints in formal are the weakest link in providing optimal quality for formal. Now you must be wondering if assume property is the only way to encode a constraint, and it is not. Let us look at the clock gating example again and look at this now from an implementation point of view, from a design point of view. One way of coding this functionality in the RTL, in Verilog or VHDL for example, could be using a multiplexer. Now a bug in an if part or the else part of the multiplexer may cause the other branch to become unreachable, automatically constraining the reachable state space of the design. Now traditionally this kind of a design issue would be flagged up by a code coverage flow. We should be able to catch this and highlight this, but most DV engineers think of these things as a design structure issue causing unreachability. Most people don't talk about these things in the way formal verification engineers would, that it is an over-constraint causing unreachable behavior. But the truth is, it is an over-constraint causing unreachable behavior. The reason I'm emphasizing all of this here is that such coding errors are actually quite common in design and auxiliary test bench code. And they're common sources of over-constraints that one should be aware. So over-constraints imply less checking of the design space and missed bugs. Under-constraints imply more, often unnecessary checking and spurious failures. Now, I was working on a project recently and someone remarked to me, hey, I'm not worried about spurious failures as someone will always review the failure. I'm more worried about the over-constraints. Now, whereas this is a valid remark, the problem with under-constraints is time wastage, both for designers and verification engineers. And if this whole thing is not controlled, it can lead to extreme frustration for everyone. Designers lose trust in verification engineers because they keep bringing spurious failures. The verification engineers lose faith in designers as they believe they don't have enough information in the first place to code the constraints. And the truth is always somewhere in the middle. The root cause for most of this is poor planning, poor specifications, and a lack of domain knowledge for verification engineers, sometimes even for the design engineers. Generally, a poor communication infrastructure between the D side and the V side of verification. And there's a method to all of this madness. We can streamline all of this. We often discuss this in our training courses, so you're welcome to come and talk to us. Let me now talk about another way of easily introducing errors in constraints. So far we've talked about assumed property and the RTL-based coding errors, right? And of course, there are more ways of coding these errors in the RTL other than the ones that I've already spoken about. But let's talk about another humble piece of design component called reset. Now, use of reset in the design is the first over-constraint that a designer applies in the RTL. And the verification engineer also has to apply the reset in the test bench. If one does it and the other doesn't, there will be a mismatch causing, again, spurious fails or missed bugs. What should not be reset must be reset. What is not supposed to be reset must not. Seems quite common sense, yeah? The problem is in practice, if you're not careful, we can easily make these errors. So in today's podcast, we've talked about clocks and resets being sources of over and under constraints, although not the only two, clearly. And we've also talked about two ways of encoding over and under constraints. There's actually much more to talk about this topic. And this is actually one of the main topics we cover in great detail in our multi-day training courses in formal verification. So what are you waiting for? Check out Aximize.com and get in touch with us. Let us show you the wonders of formal and the magic of writing constraints correctly. I hope you liked today's podcast. Please let us know by subscribing to the Aximize YouTube channel and pinging us at info@aximize.com. Stay safe, stay home, stay connected, and we will be back next week.